Hello everyone, this is Ajay Medzi from Aeronautical Engineering. In this presentation, I am going to discuss about concept video of aerospace propulsion. I am going to tell about liquid propellant rocket. What is liquid propellant rocket? A liquid propellant rocket or liquid rocket utilizes a rocket engine that uses liquid propellants. Liquids are desirable because they have a reasonably high density and high specific impulse. This allows the volume of the propellant tanks to be relatively low. It is also possible to use lightweight centrifugal turbopumps to pump the rocket propellant from the tanks into the combustion chamber, which means that the propellants can be kept under low pressure. This permits the use of low mass propellant tanks that do not need to resist the high pressures needed to store significant amounts of gases, resulting in a low mass ratio for the rocket. An inert gas stored in a tank at a high pressure is sometimes used instead of pumps in simpler small sections to force the propellants into the combustion chamber. In this figure it is showing the liquid propellant rockets, whereas the orange tank, which refers as 1, it is fuel, whereas the tank 2, which refers as 2, it is oxidizer fuel. And the point 3, which is known as pumps, here the two pumps are connected to fuel tank and oxidizer tank. When the fuel and oxidizer pumped into combustion chamber, there will be some igniter which ignites the mixture of fuel and oxidizer. Then the combustion takes place. The high and hot flames from the combustion chamber will go through convergent divergent nozzle, and it produces some thrust, upward thrust. The thrust uses the rocket engine uses the thrust to overcome the drag and gravitational force. Then the aircraft will move into the space. These engines may have higher mass ratio but are usually more reliable and are therefore used in satellites for orbit maintenance. Liquid rockets can be monopropellant rockets using a single type of propellant, or bipropellant rockets using 2 types of propellant. Tripropellant rockets using 3 types of propellant are rare. Some designs are throttleable for variation thrust operation, and some may be restarted after a previous in-space shutdown. Tripropellant rockets using 3 types of propellant are rare. Some designs are throttleable for variable thrust operation, and some may be restarted after a previous in-space shutdown. Liquid propellants are also used in hybrid rockets, with some advantages of solid rockets. Hybrid rocket engines uses both solid and liquid propellants. In this diagram you can see the rocket is moving upward. In the right side it is showing liquid propellant rocket, where it has 2 tanks, one is fuel tank and one is oxidizer tank. When the both fuel and oxidizer will pumped into combustion chamber, they get mixed, and with the help of igniter it will burn and produce high exhaust which goes through the nozzle, which produces the thrust. Principle of operation: all liquid rocket engines have tankage and pipes to store and transfer propellant. An injector system, a combustion chamber which is very typically cylindrical, and some rocket nozzles. Liquid systems enable higher specific impulse than solids and hybrid rocket motors, and can provide very high Tankage efficiency. Unlike gases, a typical liquid propellant has a density similar to water, approximately 0.7 to 1.4 gram per centimeter cube, while requiring only relatively modest pressure to prevent vaporization. This combination of density and low pressure permits very lightweight tankage. Approximately 1% of the contents for dense propellants, around 10% for liquid hydrogen. For injection into the combustion chamber, the propellant pressure at a factor needs to be greater than the chamber pressure. This can be achieved with the help of a pump. Suitable pumps usually use centrifugal turbopumps due to their higher power and lightweight, although reciprocating pumps have been employed in the liquid propellant rockets. Here it is showing that the thrust formula for liquid rocket engine. Force is equal to m dot ve plus p exit minus p inlet into area of exit. On this slide we show a schematic of a liquid propellant engine. Liquid rocket engines are used to place humans in orbit or many unmanned missiles to place satellites in orbit, and on several high-speed research aircraft following World War II. In a liquid rocket, stored fuel and stored oxidizer are pumped into a combustion chamber where they are mixed and burnt. The combustion produces great amounts of exhaust gas at high temperature and pressure. The hot exhaust is passed through a nozzle which accelerates the flow. Thrust is produced according to Newton's third law of motion. The amount of thrust produced by the rocket depends on the mass flow rate through the engine, the exit velocity of the exhaust, and the pressure at the nozzle exit. All of these variables depend on the design of the nozzle. The smallest cross-sectional area of the nozzle is called the throat of the nozzle. The hot exhaust flow is choked at the throat, which means that the Mach number is equal to 1 in the throat, and the mass flow rate m dot is determined by the throat area. The area ratio from the throat to the exit AE sets the exit velocity VE and the exit pressure PE. The exit pressure is only equal to free stream pressure at some design conditions. We must therefore use the longer version of generalized thrust equation to describe the thrust of the system. If the free stream pressure is given by P naught, the thrust F equation becomes F is equal to m dot into VE plus PE minus P naught into AE. Notice that there is no free stream mass times free stream velocity in terms in the rocket thrust equation because no external air is brought on board, since the oxidizer is carried on board the rocket. Rockets can generate thrust in a vacuum where there is no other source of oxygen. This is the specialty of the rocket. Rockets are non-air breathing engines. That's why a rocket will work in space where there is no surrounding air, and a gas turbine or propeller will not work. Turbine engines and propellers rely on the atmosphere to provide air as a working fluid for propulsion and oxygen in the air as oxidizer for combustion. The thrust equation shown above works for both liquid and solid rocket engines. There is also an efficiency parameter called the specific impulse, which works for the both types of rockets and generally greatly simplifies the performance analysis for rockets. The details of how to mix and burn fuel and oxidizer without blowing out the fuel are very complex. Uses of liquid propellants can be associated with a number of issues. Because the propellant is very large portion of the mass of the vehicle, the center of mass gas shift significantly rearward as a propellant, because the propellant is very large proportion of the mass of the vehicle. The center of mass shifts significantly rearward as the propellant is used. One will typically lose control of the vehicle if its center mass gets too close to the center of drag or pressure. When operated within a atmosphere, pressurization of the typically very thin-walled propellant tanks must guarantee positive gauge pressure at all times to avoid catastrophic collapse of the tank. Liquid propellants are subjected to slows, which has frequently led to loss of control of the vehicle. This can be controlled with slow buffets in the tanks as well as judicious control loss in the guidance system. They can suffer from pogo oscillation, where the rocket suffers from uncommanded cycles of acceleration. Liquid propellants often need large motors in zero gravity or during staging to avoid sucking gas into engines at startup. There are also subject or vortexing within the tank, particularly towards the end of the burn, which can also result in gas sucked into the engine or pump. Thank you.